Today, well, welcome to discussion hour. Peri suggested this at the very beginning of the semester because I know a lot of UTIG folks and main campus folks are headed to LPSC in a couple of weeks. And so I figured this would be a great practice presentation for those that are giving oral talks. And so first up, we're gonna hear from Soraya. And then we're gonna hear from Peri right after that. And so I guess a quick introduction for Soraya before she starts. Soraya is a second-year master's student, hopefully manifesting PhD soon, at UTIG, working on modeling the post-impact hydrothermal system at Chiculub crater by exploring factors that can affect its lifetime. The mechanisms driving the system have implications for understanding the rebound of life after the impact and can allow us to make influences on similar habitat-inducing systems on early Earth and other planetary bodies. So with that, let's welcome Soraya.
Hello, everyone. As Michaela said, LPSC is a few weeks away, so this is a very preliminary presentation. So with that being said, let's start. So first, why model Chiculub's hydrothermal system? One reason is to constrain the extent and duration of the system. And if we look at the seismic profile here, oh my gosh, we see these upflow features. And these perturb the Paleocene-Eocene boundary, which was 10 million years after the impact. And if these were caused by the hydrothermal system, that suggests that it potentially could have lasted that long, which is much longer than the current estimates that we have. And in addition to that, the Chiculub impact is linked to the end Cretaceous mass extinction. So by understanding the mechanisms that drive the system, we can better understand how life rebounded after the impact. So first I want to talk about some previous models. This one in particular is a popular one by Abramoff and Kreng, and they formed this before there was the IODP Expedition 365. So a lot of the data they have is based on boreholes that are towards the outside of the crater and from previous models and data. So this is the input geometry that they use for their model. It's a hydrothermal model, by the way. And this is also the initial temperatures that they use for their model. And these are their results. So the central impact melt sheet heats the material above it, and that to about 1200 degrees Celsius, and that allows it to become molten. And also on the right side, they have the convection, and we can see that there's fluid infiltration to great depths in the crater cavity and also within the impact breccias above the melt sheet. As the system cools, the impact melt sheet becomes more permeable, allowing for more infiltration within the system and extending the extent of the hydrothermal system. And they say that the duration of the system is 1.5 to 2.3 million years old based on assumed permeabilities. But one thing that they use for the definition of the lifetime of the system is the time it takes to reach 90 degrees Celsius within 1 kilometer of the surface, which I think is kind of vague because the surface is the quickest to cool and there could still be circulation beneath the surface. So taking this model into account and all the new data we have, this is the new data that we have that we're going to use to constrain our model. So thanks to IODP Expedition 365, we have specifically permeability data. An interesting thing that we found is that the swavite layers have lower permeabilities than previously thought, and the peak ring granite has higher permeabilities in the range of about 9.8 by 10 to the minus 1 million darcies. And the permeability is an important factor for convection because that's how fluid is able to flow within the system. And also from Expedition 365, we have seismic data, and we can use this to map the subsurface and get a better idea of the geometry within the central crater and the peak ring. And then we also have thermochronologic data. And this one in particular shows zircon and helium data that have ages as young as old as 14 million years younger than the impact, if that makes sense, which suggests that the hydrothermal system lasted potentially up to 14 million years after the impact. So with all this new data that we have, we can create our model. So this is the geometry that we came up with based on the seismic data. We have the pre-impact sediments, the peak ring granite, the melt sheet, and the 2 swavite layers. So for the physical properties, we have temperature and porosity, which we based off a previous model, a previous ISAIL model, and we used that specifically for the peak ring and for the pre-impact sediments. But for the melt sheet and the swayite layers, we use data that we have from the drill core. And when it comes to permeability, they did some experiments on samples from the borehole, and we got a relationship between porosity and permeability, and we use that to create this permeability field and also include an exponential decay with depth. So adding all that into our model, these are the results that we get. So the white lines here are streamlines indicating fluid flow, and in this case, they're going in an anti-clockwise direction. So an interesting thing that we saw is that these pre-impact sediments, because they've been thrust downward, act as a conduit for fluid flow that distributes fluid from the surface and brings it down to depth, and then redistributes it throughout the peak ring granite. And then because the granite is so close to the melt sheet, which is the main heat source for the system, it then further drives convection. And also another interesting fact is because the swayite layers have a much lower permeability than we expected, it sort of acts as a blanketing layer over the system and helps keep it within the subsurface, if that makes sense. But our peak convection happens within the first tens of thousands of years, but by the time we reach 300,000 years, everything is pretty much slowed down. And this is the furthest time scale that we were able to run our model to, which is much, much shorter now what we think it should be. So moving forward, we wanted to do a few things to help extend the lifetime of our model. And just in this figure here, the blue line is the temperature decay with time in our model compared to the current thermochronologic constraints that we have, and it's much, much shorter. So we want to be able to add radiogenic heat production, a temperature-dependent thermal conductivity, and also gradual sedimentation with time. So starting off, we have radiogenic heat production. So luckily, during Expedition 365, they did some downhole logging and we got these natural gamma ray measurements. And using this equation, we can get heat production. But I also have the porosity plotted here and they seem very much related. So one thing that I need to do, there's an equation I need to use that takes into account the void space in the rock, so we can see how much of the porosity is affecting the heat production. But these average values that we have, especially in the granite, is within 1 order of magnitude of the current estimates in the region. So we're pretty good on that front. Next, we have the temperature-dependent thermal conductivity, and this figure here shows some results from a study that was done on rocks from various types of crust. And the type that we're interested in is the upper crust. So based on the samples that they used in this paper, we can calculate the temperature-dependent heat capacity and then thermal conductivity. And in this figure, the red and orange lines represent the 2 granite samples that they had, but the second granite sample is closer to the upper crustal relationship that we want. So after getting a curve fitted to this data, we can then apply that to the thermal conductivity values that we have from the borehole and then incorporate that into our model. So when a cell reaches a certain temperature, we can use the relationship to change accordingly. Next, we have the sedimentation with time. So from the sediment cores that we have and nanofossils and forams in the sediment cores, we have an idea of how fast sedimentation happened within the first 18 million years after the impact. And we can see that it started off pretty slow early on and then rapidly increased in the Eocene. However, after this time period, we don't have much of a constraint on how fast the sediment was deposited. So we decided to use this linear relationship to get to the current sediment levels that we see in the borehole. And then using that, this is the new geometry that we hope to get. So the idea is that with varying time sets, we add a new layer of sediment. And hopefully that can help trap some heat within the system. Yeah, and that's about where we're at right now. Hopefully by the time LPSC rolls around, we have results. But moving forward, some more things that we want to consider is when the melt sheet is molten, there's no porosity or permeability, but as it cools, it gets more porous and assuming more permeable. So we're hoping that we can figure out a way to do that, because the longer it's impermeable, the less heat is lost within the system due to convection. And then we also want to incorporate the basal heat flow, which is linked to the radiogenic heat, and also the latent heat of crystallization of the melt sheet, because that can also help extend the heat within the system. And the longer that the melt sheet stays molten, the more heat it can provide to the system. And then using the results from those models, we're hoping to be able to plot some temperature contours that can give us an idea of the location that microbes could potentially survive within the crater as the system evolves. And that is where we're at. That is where we're at.
Questions for Soraya?
Why did you pick a linear relationship to kind of extrapolate on the segmentation?
That's what Mark suggested. And I went with it. I think we just don't have like a good enough idea.
Does it match up with like the thickness of the sediment today when you just,
Yeah,
Okay.
yeah, that's what we did, yeah.
that's good at least.
For the mineralogy, what is swayvite?
Swayvite is a melt bearing breccia.
Okay.
Yeah.
So this is a 2D model,
It's like radial.
it is right.
Yeah.
Okay.
Does, for your heat, like, inputs, is that, did you just set that, or is there some kind of like diffusion law showing how the heat from the input changes?
It is a heat diffusion law, yeah. It definitely is. I can't say exactly right now. But you know,
Do you know how it would change if you like have slightly different diffusion of heat, or is it like calibrated to the,
I don't, it's not,
is it calibrated to the thermocol? Or?
it's not calibrated to the
Okay.
chemical right now, so I can't really say how it would change if we changed it. Yeah.
Sophia, you wanna unmute?
Yes. How how important is it like where you picked this cross section? Because like when you were showing your results of the heat flow and like hydrothermal system, yeah,
This one?
yeah, like this, yeah, like these, like, because how important is it that you picked this cross section? Because then going back to your last slide where you're showing that gravity anomaly map, like it looks like there are very different features going from like maybe northwest to southeast versus just like east-west across this crater. So like why did you pick this location, and like how important is it that you like are only selecting one cross section versus maybe looking at like many different cross sections?
Well, this geometry is based on like the seismic data that we have. So this is kind of the best idea that we can have, but it's a radial geometry in the model. So how do I describe? So kind of like a similar, it's kind of like a cylinder, if that makes sense. We just assume that if this is half, if this figure is, where's my mouse? If this figure is half, then it spins around and makes a circle, if that makes sense.
Oh,
It's-
okay. That's
yeah.
interesting. But
Yeah.
how symmetrical is that in reality? Is the crater?
Not- Definitely not that symmetrical at all.
For sure.
I think this is the best we could do with the data that we have. I feel like it would be much more complicated if we wanted to do like a geometry closer to what's actually there, because then it'll probably have to be like a 3D model.
Right,
That makes sense.
okay.
But also the heat, the radiogenic heat stuff that you're talking about, that's based on the borehole, which is right around here. Hopefully you can see my mouse right now.
Yeah, okay, and then these lines like indicating stream or like flow, like fluid flow, like how do you read those? Like
This is-
lines closer together or more more flow or?
Yeah, that's exactly how to read it. The closer to the closer together they are. Each line is a different. Each line is a different, I want to say velocity, but the closer together they are, the more vigorous the convection is. Yes.
Okay, and then why is the convection so fast, sorry, in the little tip of the like sediment block going down?
It's a discussion.
Well, the sediment has like really high porosities, so I just assume by the time it reaches all the way down here, the only place it can now go is through the granite, and that's why.
Oh,
it's
okay, that makes
redistributed.
sense.
Yeah,
Okay, thanks, Pooks.
no problem.
One more question.
Just kind of a follow-up, has anybody done a reconciled gravity seismic reconstruction of Chiculub?
I think, I know they had a seismic characterization by Gail Christensen. I want to say 2019.
Okay.
Yeah.
What session are you gonna be in?
I can't remember the name of it. I think it's called striking modeling impacts across the solar system.
Okay.
Something along that. It's on the Monday.
Monday.
Yeah. My talk is at 9:55 AM.
Oh,
Yeah.
first day.
Yeah.
Wait, I had a question. More of a comment, actually. What's the legend for this?
That's great.
Can you put it next time?
Yeah.
Thanks. I mean, you explained it pretty well, but I was just like, yeah. Perfect. All right, let's thanks for one more time.
Woo!
Next up. Oh, you didn't see that. Next up we have Peri.
Can I ask when you downloaded the slides? A lot has changed over the past hour or two.
I downloaded at 12:40 something. Should I look it up? Okay.
Easy enough, yeah.
Okay, intermission.
Yeah.
Chat and eat snacks. Okay.
Yes. Yes.
Can
I have another glass?
Where's my email?
The brownies in the there. Can I have your phone?
Yeah.
Yeah.
Was it on my phone?
Will you look up the sign of the some Instagram post?
Yeah, that's sorry. The vintage.
I'm gonna go and I'm gonna leave it. Is that the like? Yeah, you want to come on? What is this? Tonight at 6:15 at Vintage. Maybe.
No.
Yeah.
Everybody's really chatty and all of a sudden they're like, it's me kid, and it's like, it's really.
There's no link. Nope.
I think if you.
What is it?
If I replied to this one. I sent you this, I was like, here's my bio, and then. Yeah. We have to cut them up for the baby, because it really showed it on one.
If you don't working. Here we go. Okay, then you can just present from here, right? Perfect. No, no, no. Oh my god, wait. It's not. Slideshow. Oh, wait, hold on.
Just click the slideshow.
That was great, sorry. Okay. Introduction for Dr. Peri. Would you like the mouse? Sure. A little pointer. Thank you, Linda. Amazing. Dr. Peri Ann Johnson started as a postdoc here at UTIG last September, where she's mentored by Dr. Krista Sunderland. She finished her PhD in planetary science last May at UC Boulder with a thesis titled Modeling Pluto's Atmosphere and Volatile Inventory Throughout Time. Peri studies planetary ices and atmospheres through the solar system, and while at UTIG, she has branched out to the study of ocean worlds as well. Let's welcome Peri.
Okay, hi everyone. My slides are also like a little bit rough. Like Soraya said, since LPSC is still like 2-3 weeks away. But I'm going to talk about sort of an in-progress project looking at seafloor erosion on Enceladus and Europa, and really ocean worlds in general. So some of the like motivation behind this project comes from looking at Earth's seafloor, which has some like really big, amazing canyons that are carved on like the edges of continental shelves. So I'm showing Monterey Canyon off the coast of California here as an example. And then sort of the like, you know, a converse to that is there are parts of Earth's ocean that are just like absolutely covered with sediment layers, up to like 10 kilometers thick. So there's just so much sediment coming out of Earth's rivers, and from like biogenic sediment from organisms that die and then fall onto the seafloor. And so this is sort of the regime of Earth's seafloor, but on ocean worlds, they don't have this continental sediment because they don't have continents. And I am not even going to touch the question on if they have biologic sediment or not. That is a question for someone else in a different talk. So we wanted to investigate what erosion might look like on seafloors in this very different regime. So the sort of first pass at doing this, we were following the work of Devin Burr, who had looked at erosion on Earth and Titan. And so that we adapted that model to ocean worlds, to Europa and Enceladus. And in this plot, I'm showing a measure of the velocity of the flow on the y-axis, and the size of the sediment on the x-axis. You can see the color bars there, and if you are above that line, your sediments of those size are able to be transported by flow of that speed. And if you are below it, no motion occurs. And so you can see for these ocean worlds, the threshold for motion or for transport to begin is much lower. So lower flows are able to transport grains of the same size, which gets you really excited that the seafloors of Enceladus and Europa could be very vigorous, very sedimenty, transportable surfaces. I will note that like one caveat is that this frictional velocity that I have here on the y-axis is not really a true measure of the flow speed. The actual flow speed is something like a factor of a few tens higher than what I've shown here. So for Enceladus, for example, the flow speed needs to be higher than about 2 centimeters per second in order to transport grains that are sort of a typical sand size of 0.1 millimeter or so. And this velocity is sort of in line with the range of velocities that ocean circulation models have predicted for Enceladus and Europa, somewhere along the order of centimeters per second, is sort of in the ballpark of what we think the bottom currents could be on these worlds. So once the sand particles or particles of any size get into motion, we kind of think of 3 classes of transportation or 3 stages of transportation that can occur. Really, it's like a spectrum between all of them, but For the sake of this talk, we'll talk about them in three categories. The first of which is bed loads. These are particles that never get like truly lifted all the way off the ground. They kind of roll or slide, or saltate, which is like little jumping motions. And so they're just kind of being moved along the bed that way. If the particles are slightly smaller, they can be transported as suspended load, which are particles that are held aloft mostly by the turbulence in the flow. And so they'll be aloft for a while and then they'll fall back down. And that process can repeat. So it's sort of like an extra long saltation jump, if you will. And then the smallest particles get transported as wash load, which are just like totally along for the ride. They're just moving at the same velocity as the flow. And in this talk, I will focus mostly on bed load. So that bottom one. So again, following the work of Burr, we can calculate the threshold for motion in each of these three transport stages. So now if you are, if you're below the bottom line, your sediment grain are not going to be moving between bed load and between the bottom line and that second line. I have a mouse. So between like in this region, particles of that size are able to be transported as bed load, and so on as you move to higher velocities. So I'm showing Earth first just to walk through it, and then I can overlay Enceladus. And so you can see once again that slower flows are able to transport grains. That's the same thing we saw from the previous slide. But I will also say that larger grains are able to be transported as suspended load on Enceladus. So if you look at kind of the like bifurcation point, here for Earth, the transition between bed load and suspended load is happening at around 0.1 millimeter grains, where for Enceladus, it's happening almost an order of magnitude higher. And so that means that any particles that are smaller than about 1 millimeter on Enceladus are just not able to ever be transported as bed load. They will, as soon as they start moving, they'll be into the suspended load regime. And I don't remember if I said this for the slower flow part, but this is really a consequence of the lower gravity of these worlds. So there's more or less an order of magnitude decrease in gravity between these three worlds. I mean, Earth is 10 meters per second squared, and then Europa is about 1, and Enceladus is about 0.1. And I will show Europa on here again, just for just quickly, because the plot gets very overwhelming with all these curves. But Europa is kind of the in-between case again, because the gravity is in between. So the sort of a final measure that becomes important for erosion is the settling velocity of these particles, which again is just dependent on the gravity of the different worlds, since they're all water. The viscosity of the fluid comes into play as well. But you can see that for Enceladus, especially, the settling velocity is something like a factor of 10 lower. So these particles will stay aloft for longer, and when they do eventually bash back into the bedrock, they will do so with a much lower like kinetic energy. So still to come is understanding if this lower settling velocity will translate into a lower erosion rate at the seafloor of Enceladus and Europa compared to Earth. And hopefully it will answer that question before LPSC, but the sort of general idea for bed load abrasion and calculating an erosion rate from that is dependent on these three multiplicative factors. So some sort of quantization of the volume of material eroded per impact, and then the impact rate, so how many sediment grains are smacking into the bedrock as a function of time. And then finally, how much of the bedrock is exposed. So if the bedrock is already covered with a thick layer of sediment, then that sort of diffuses the energy of the saltation bed load impacts, and that will lower your erosion rate. So that comes into play as well. So yeah, this will be future work to finish up. And the settling velocity affects 2 out of these 3 rates. So the fact that the settling velocity is a lot lower on Enceladus and Europa might spell trouble for carving canyons on Enceladus' seafloor. There are like lots of avenues I think that this research will be applicable to. So understanding both the rate of erosion and deposition on the seafloor of ocean worlds, and especially understanding the characteristic sizes involved. Will tell us things about the shape of the core, and the porosity of the core, the specific geometry of the rock-ocean interface, slopes that could be expected, understanding how much material is traveling as wash load or suspended load, and dissolving into the ocean fluid itself, will tell us things about the composition of the ocean, and also about the bioavailability of any bedrock material. So if organisms are needing these minerals, that's important. And I'm interested in hearing thoughts on other avenues that this could be applicable to. And so I'll just end things with a summary of what I've said so far. The sort of key takeaway is that due to the low gravity on these small ocean worlds, lower velocities are capable of transporting sediment of the same sizes relative to Earth. And future work will involve quantifying this erosion rate to understand how much erosion is actually occurring, and also understanding where the transported sediments end up. So are they all transported towards the equator, towards the pole, some other location? Where are they ending up? And I will just finally end by saying that our model is generic and can be applied to your favorite ocean world. So if you're interested in one besides Enceladus and Europa, that's doable. We can work more on that. So that's all I have.
You first.
Does the depth of the ocean have any effect on these velocities? And if so, how?
I think it probably definitely does have an effect, and it is not an effect that I have quantified at this point. Yeah, the depth of the ocean on ocean worlds is much, much deeper than Earth's ocean, because Earth's ocean is 4 kilometers deep, something like that. And ocean world thicknesses can be, I don't know, 100 kilometers thick. So I think that is definitely something that will be different, and will affect the erosion, and is not something I have quantified at this point, but yeah.
Okay, well, it's gonna sound so dumb, but has anyone tried to infer from either radar or any other satellite to look at the bathymetry on any of these ocean worlds, or do people just have their crazy imagination to map things out?
I think right now it's just crazy imagination, but maybe, yeah, I don't know if Elizabeth or Krista know anything more. Yeah.
Okay.
Yeah.
Yeah, cause I don't know.
Yeah, are there seamounts?
Right.
What's going on this
Right,
floor?
or is it's all just gravity and turbulence
Yeah.
dynamically moving things around?
We gotta send a little probe there to drill through the ice shell
Mhm.
and swim around.
Mhm.
That's the answer.
Yeah, speaking of unconstrained environments, the question is so you can have slower currents, it's more easy to move sediment around.
Yeah.
But, I mean, what kind of, velocities, what kind of driving forces do you expect to be driving currents on an ocean world where you have ice covering the whole thing?
Yeah, so because you're getting at the fact that on Earth, a lot of the current is driven by atmospheric circulation. Yeah, that's a great question that I think Krista has some sorts of answers to. So there are models of what the circulation flows should be on ocean worlds. Yeah.
Yeah, so there's some kind of ocean models that have a very wide range of what the flow speeds could be. They can kind of go from millimeters to meters per second to give you a sense of the range.
Okay.
So I think centimeters per second is kind of a more reasonable value in that possibilities.
What's driving that flow then? Is it tidal forces exclusively? Is there something else?
So there's a few different ways that you can drive flows, thinking about Enceladus for one, you have, tide being one component, and you could have vibration as one component, but you also have like potentially hot seafloor, so that can lead to buoyant flow. But then you also have salt that's being rejected in areas that you have the ice shelf freezing. So you have another buoyancy source. Then you also have to incorporate within these regions that are melting, so you have like fresh water, so you have like this thermal compositional
Okay,
circulation that occurs as well.
all right.
And to make it even more fun for Europa in the Jupiter system, you can also have currents being generated by Jupiter's magnetic field because it's a salty ocean, so you have many ways to
All
drive
right,
flows.
cool. Yeah, not as stagnant an environment as I was expecting.
Yeah, it's like super fascinating and.
I think I'd seen Alice. next.
Oh, I was gonna say, so the model you have here is kind of like, taken or like, there was a tiny one before, and how much did you have to kind of like modify that apart from changing the gravity?
So I looked a lot for like Titan ones that I used it before. So this Burr one applied it to actually Mars and Titan. Because a lot of the like Earth focused models for erosion have gravity like baked into it, and so it's not easy to change to a new planet. And so this like Burr model specifically went through the trouble of sifting through the literature to find one that has explicit gravity, so you can change that and put it on different planets. Yeah, so that's sort of like the changes that have had to be made. Yeah, not a lot of changes besides just changing the parameters that go into it, the gravity and the types of particles. Although for right now, I'm assuming like quartz grains, which is like earth sand. I think there's maybe an argument to be made that more of like a basalt type grain would be better for the seafloor of these worlds. But yeah.
Cool. Have you had a chance to look like gypsum or anything?
No, I haven't considered anything else but gypsum. Okay.
Yeah, basically.
Okay. Yeah.
Does the model have any parameterization for the stickiness? Which kind of gets this model?
It uses like empirical experiment derived like friction parameterizations for like the particles scraping along in channels with the flow. And so I think some sort of like stickiness is probably involved with there, but it's not something I have like adjusted at all. Yeah.
I was gonna ask about density, and you said that it was quartz grains, like right before I asked. I guess I'll just kind of. How much is like density like proportional or inversely proportional, so if you change your. It's okay, I know. But
yeah. I'm trying
what
to.
would you expect if you use quartz grains and say it was maybe like an iron grain or like a really fluffy kind of gypsum grain, maybe? Did you expect it to change much?
It doesn't change a huge amount. So this Titan paper that I base this on, I'm picturing like their curves for Titan, because they investigated both water ice grains for Titan and like super not dense organic particles. And the gravity would still be like overwhelming deciding factor. But density definitely plays a role. Yeah, I think going between like quartz and basalt is not going to be a huge difference. But if it was something between like quartz and something incredibly fluffy and porous and
Marshmallow.
a marshmallow would be a lot more different.
Martin has a question. If you want to unmute.
Hi, Peri. That was such a great talk. This is super interesting. I was just wondering, and it may be not like relevant, I don't know. What role would like ice grains have in this? So like you're looking at like basalt, like more rocky like things. What like would you expect, or like do you plan to kind of look at like what like the ice is doing, or like where does that fit into this, if at all?
That's a good question. I think the answer is that there won't be ice down here at the seafloor. Cause this is where the ocean is like warmest and then it cools as you go up towards the ice shelf. So I think like ice grains would not survive, down at the seafloor. Yeah, I think that is my uninformed answer. My guess.
That makes sense. I was wondering if that's what it was, like, because I don't know, when I think of like these worlds, I feel like a lot of the times it's like usually like ice side or like it's water ice that's like being looked at, or just like let me not say water ice. I literally don't know anything about that. Like, let me not say that. But I feel like it's usually like a focus on ice grain. So I was kind of interested to see that you were using like rock, like quartz or basaltic type grains to look at this.
Yeah, so this is more at the like the interface between the bedrock, the seafloor, and the ocean. But maybe there is some interesting erosion happening up at the bottom of the ice shell as well. And that could be more like, I don't know, dislodged little ice grains bashing into the bottom of the ice shell and causing problems.
It may be interesting to see like the fallout velocity, if any like thing is like stuck in there.
Mhm.
I also like don't know, I mean, you have 100-kilometer ocean, so I don't know how that's gonna circulate through and affect erosion.
Yeah, so like falling out from the bottom of the ice shell, you're saying, all the way down? Yeah. I think that is like something that has been looked at, because there's like silicate particles in Enceladus's plume. And so there's like, it's like, did these silicates come from the core and made it all the way through the ocean and then were ejected out into space? Like, that's crazy if true. But I think the result of the paper that I read was like, yeah, here's the conditions under which it could be true. So I guess the reverse of what you were saying, but there is some sort of interaction between the seafloor and the top of the ice shell.
Shut but could there be methane clathrate down there? And do methane clathrates behave in a totally different way that is not this?
Clathrates are the new giant impact, I swear. Out clathrate.
I'm gonna be interested, I don't know really about clathrate, so apologies. but-
Yeah, when I've heard of like methane clathrates before, they form like in like ices and whatnot, right? So would that again be like a methane clathrate like at the bottom of the ice shell, not at the bottom of this ocean?
Well, on Earth, you could form them at the sea floor because the phase curve for methane clathrate is a bit different from water ice.
Okay.
Depend on it's a combination of pressure and temperature.
Yeah.
Okay.
Seafloor and-
Yeah,
But you can find them as low as 200 meters above
okay, 200 meters.
of the water depth. Right.
Okay, so, yeah, it was not something I have thought about at all.
0.1 seems so low that I'm surprised. I don't know about like other planets if it is lower. What do you have a sense of what would be the lowest gravity that you could still get in the ocean?
Oh,
Is that kind of they are kind of generally increasing with their
Yeah.
ratio, but
Yeah.
it seems like that, like, what's the boundaries of that?
but I don't know. Enceladus is like one of the smallest ocean worlds, lowest gravity ocean worlds.
Oh, yeah.
So,
It's like the size of Spain, entirely.
Really? That's-
250 radius, 250 kilometer radius is really, really small. So, yeah.
Small.
It's a baby moon.
Yeah.
A baby moon.
And it like plays above its brackets. Like it has a lot of attention and interest for being such a small little speck. Like rightfully so.
Maybe that's a side of things to come, like what if, Uranus, Jupiter, and Probe gets there and it turns out that all the small moons are doing weird stuff, we just haven't noticed.
Yeah.
Miranda's wacky as hell on it.
Yeah, Miranda's bizarre and Ariel's surface is unusually young.
Yeah.
Yeah, cool stuff to come.
Let's thank our speakers.